Assalamu alaikum dear students, we're back with another video lesson. In the previous video lesson we were talking about moment of inertia, and we said moment of inertia, it is the tendency of an object that is rotating to resist the change, and it is rotational motion, and it was measured in kilogram meter squared. We said also moment of inertia, it is a scalar quantity. In that case, of course, it cannot be zero and it cannot be negative as well. Moment of inertia highly depends on the mass distribution. And we also said that the closer the mass from the axis of rotation, the less the moment of inertia, the easier it is going to rotate. And in the other side, of course, or on the other side here, the further the mass from the axis of rotation, the larger the moment of inertia, and thus the more resistance to rotate the object. In other words, you can say the less the angular speed. And then we talked about the moment of inertia for different shapes, and then we ended up at question number 4 here. We said the moment of question number 4, that is a chapter review question. What does it say? It says the moment of inertia for a regular object can never be larger than 1 times, or just mass times the radius squared, where m is the mass of the object, r is the radius or the size of the object. Why is this so? And the question itself gives us a hint, and also says which object has a moment of inertia which is equal to mass times the radius squared. And I've just mentioned that in this case we said that moment of inertia highly depends on the mass distribution. So if we look about which equation of moment of inertia has 1 times or just let's say mass times the radius squared, we said one of the shape that we have, it is one of the shapes that we have, it is a ring, okay? So, and you can see that for the ring, the mass is distributed very far from the axis of rotation. And another shape that we have, it is a point mass. If a point mass that is rotating in a circle, isn't that the furthest where the masses can ever be from the center or the axis of rotation? Yes. So we don't have any other shapes, let's say, where the mass can be very far from the axis or from the center of rotation, whether if it is a point mass, or it could be a ring where the mass is, or it could be even a thin hoop, let's say, about the center perpendicular that is passing through the center of the axis, or the center is the axis of rotation. In this case, you can see the mass is very far from the axis of rotation. Do we have any other shapes where the mass is even further from this shape? The answer is no. So in this case, this moment or this equation, it is going to serve the upper limit of moment of inertia of an object. And all the other shapes that we have, if you remember, this is clearly one. Other shapes we have, let's say for a disk, which is 1 over 2 mass times the radius squared. We have for a solid sphere, that is 2 over 5. We have for thin spherical shell, that is 2 over 3, and then other shapes as well. If you look at these each one of these are going to be less than 1. In other words, we can say this would be the upper limit of the moment of inertia for an object that it can ever have, let's say, or has. All right, that is, so this is the reason why we can say this is because this one represents the moment of inertia of a point mass. It could be a point mass or a ring that is at maximum distance from the axis of rotation, which is clearly serving as the upper limit of an object, or for an object with the maximum distance from the axis of rotation. In that case, that'll be the maximum moment of inertia. Okay, clearly if you increase the radius and the mass, that'll be even more, but the point is, do we have any other shapes where the mass could be this far from the axis of rotation? The answer is no. All right, now we have a study tip, and this study tip, of course, it could save 2 marks. It could save you 2 marks. Says if a baseball bat is mentioned, the closer the grip from the end, the bigger the length of the bat, which in this case the mass will be further from the axis of rotation. In that case, the moment of inertia will be larger, okay? But if we, let's say, so in this case, the less the angular speed, what happens if we hold or grip the bat closer to the center? Let's say this is the bat we have. We know that the bat is not as uniform as this one, but this is just for the sake of an example here. If you hold the bat, let's say this is the center of the bat at this point here, even though that is not where the center of mass, because one side of the bat is heavier than the other side. But for the sake of the example, that is the center of the bat. If we hold, let's say you're a point here, okay? If you're holding this one closer to the end, you can obviously see that the length of the bat, it is going to increase. And if the length is increasing, you can see that the mass will be far from the axis of rotation. So if the length increases, we can say the moment of inertia increases because now the mass is far from the axis of rotation. If we consider this as the axis of rotation in that case, then if the moment of inertia increases, then the angular speed would decrease. In other words, we can say it would be way more difficult to rotate the bat if we hold it or grip the bat closer to the end here. But what happens if we hold or grip the bat closer to the center? If we hold it closer to the center, the length of the bat, it is going to become less. If the length is less, now we can say the mass is closer to the axis of rotation, so moment of inertia, as a result of that, it is going to decrease. And guess what happened when moment of inertia decreases? Then clearly the angular speed increases. We can say this bat will be easier to rotate or turn because now the moment of inertia is going to be less. And if you don't understand this one, once you hold the bat or grip it closer to the center, that'll be the same or similar to a thin rod where the axis of rotation is right through the center, and we had 1/12. The moment of inertia for that, it is 1/12 times mass times the length squared, and that is what we have. But if we hold it closer to the end, now if the end is the axis, or consider the end to be close to the axis or the axis of rotation, then we can say the moment of inertia, or the equation for moment of inertia would change to 1/3 times the mass times the length squared here. So this is the reason why, but I should have wrote this one here. We can, if we hold it close, that'll be moment of inertia, that'll be 1/3 times the mass times the length squared, so that you don't get confused. And then moment of inertia, if we hold it close to the center, will be similar to 1/12 mass times the length squared. Once again, the center of mass of the bat is not at the center because one side is heavier than the other side. But if you understood this, that is great. If not, this can help you a little as well. So just remember now, you can write this as a note for yourself. If we hold the bat closer to the end, the length increases, moment of inertia increase, angular speed decrease, so it is going to rotate slower. If we hold it closer to the center, the length decreases. We can say the length from the axis of rotation because now you have length from both sides, but the total length, or the length that is considered, the one that we consider for the moment of inertia, so that would be closer to the center, so the mass will be distributed closer to the center, moment of inertia would be less, angular speed would be more or bigger. In that case, it is going to rotate easier or faster. Okay, I hope that was easy enough. Now, let's see if we have any questions related to this one here. All right, so this is the study tip that I was just telling you about. If L is big, that means moment of inertia is big, then angular speed is going to be small. We can say small rotation and vice versa too. All right, now we have question 10 says, at a circus performance, a juggler is thrown 2 spinning clubs. One of the club is heavier than the other one. Which of the following statement is true? All right, now you do remember what we have mentioned about if we throw a stick into the air. Now there are 2 sticks, one of them is heavier than the other one, and also don't forget, we said this stick has center mass, center point, and 2 ends as well. You can call it end A and end B. We said both ends are going to rotate or spin about the center of mass, but the center of mass itself, it is going to follow a parabolic path. Okay, let's see the options here. The first one says the smaller club is likely to have a larger moment of inertia. Is that true? The answer is no, because we know that the larger the mass, the more the moment of inertia, because these two are directly proportional from the equation of moment of inertia, which whatever the shape you're using here, times mass times the radius squared. So if the mass is increased, the moment of inertia increased, but it contradicts with this one, so option A is incorrect. What about B? Says the ends of each club will trace out parabola as the club is thrown. Is it the end that is tracing out parabola, or the center of mass? The question says the ends will trace out parabola. Again, that is incorrect because the center of mass trace out a parabola. The third option says the center of mass of each club we'll trace out parabola as the club is thrown, and that would be the correct answer. So option C, here it is going to be the correct one. All right, now we also have question 11. What does it say? It says, when the juggler in the previous problem stands up straight and holds each club at the arm's length, where would his center of mass would be? Consider that I have, let's say, 2 pens. Where's the other pen? I think I had 2 pens. Obviously, I don't have it with me. Consider these are the 2 clubs. Each one of these are held at the arm's length. If I extend my arms like this, clearly there are two clubs. One of them is heavier than the other one. So do you think the center of mass, so what exactly happens here? It says, where would his center of mass would be? Do you think the center of mass now it is going to be exactly at the center of my body? The answer is no. If you remember in the previous lessons, we said that the center of mass will always be closer to the heavier side. I hope you remember that one. Okay, so once again, if I hold 2 clubs here, one of them is heavier than the other one. Do you think the center or my center of mass will be right at the center of my body? The answer is no. So let's see what the options say. The first one says it is located at a point exactly in the middle of his body. Because it says exactly, that is incorrect, so option A is incorrect. B says slightly to the side where he is holding a light club. Is that true? No, center of mass will be closer to the side that is heavier, not to the lighter side. Okay, so that is also incorrect. What about C? It says slightly to the side where he is holding the heavy club, and that'll be the correct answer here. All right, following this, we have a Wazari question. What does it say? It says baseball players sometimes hold the bat closer to the center. And remember the note we just went through? So why do they hold the bat closer to the center? How about if I, all right, let's just start from A. It says to decrease the bat's moment of inertia. We said if we hold it closer, to the center, okay, assume or consider this is the bat, and this is the center. If we hold it closer to the center, we said the length decreases, moment of inertia decreases, so angular speed is going to increase here. But this point, where part A says to decrease the bat's moment of inertia, so this is a good option. Let's keep an eye on this. B says to increase the bat's moment of inertia. If we hold it close to the center, the length decreases. So do you think the moment of inertia increases? The answer is no, so not option B. What about C? It says to keep the bat's moment of inertia constant. If we increase or decrease the length, the moment of inertia is going to change, so it is not going to be constant, so not option C as well. It says D says has no relation with the moment of inertia, and we know that is incorrect, so now the only correct answer is option A at this point here. All right, next time in Wazari, maybe they'll add the angular speed as well. Now this point here, we are at a, you can say, at a new concept, and that is we can say rotational equilibrium. This is one of the main concepts that we have in chapter 2, beside we can say moment of inertia, because hereafter we might need this a lot. So I hope you're paying enough attention at this point. What is rotational equilibrium? And then how are we going to study this? Let me give you an idea about rotational equilibrium. First of all, in order for something to be at equilibrium, let's say that has to be at translational equilibrium, all right, and also it has to be at rotational equilibrium as well. So what exactly those concepts or those concepts or the thing that I just said means here? For something to be at equilibrium, let's just say if the object is moving forward or backward, it has to keep moving. If it is moving, it has to keep moving in a straight line at a constant speed. It shouldn't increase or decrease. That is called translational equilibrium, and you've studied that in grade 11 as well. I'm going to explain more in a bit. And then what about for rotational equilibrium? If an object is not rotating like at rest, it must remain at rest, or if it is rotating, it must rotate with a constant angular speed. That is when it is called rotational equilibrium, because if it is rotating and speeding up or slowing down, in that case, that means there is a net torque on the object. This is why it is rotating faster or slower, and we cannot say it is at rotational equilibrium. All right, now, make sure what I'm going to write on the board, you take some notes too here, or it would be best if you write it down as well. We can say for an object to be at equilibrium, we can say object. For an object to be at equilibrium, for an object to be at equilibrium, remember this. We'll say there are two conditions for the object, in order to be at equilibrium. If the object is at rest, it must remain at rest. It must remain at rest. That's first. Second, if it is moving, it must keep moving. Let's say it must keep moving at a constant motion. At a constant motion. And we're going to talk about this constant motion here, whether that be translational or rotational. But let's get back to this. We said, in order for something to be at equilibrium, if the object is at rest, it must remain at rest. In other words, we can say, if an object is at rest, clearly that means the velocity of the object is zero. If the velocity is zero, we can say the change in velocity is zero because it is staying at rest. If that is the case, then we can say the acceleration of the object is zero. And if the acceleration is zero, we can say the net force on the object is zero because F net decata, or it is equal to mass times acceleration here. If the acceleration is zero, then the net force is zero. If that is the case, the object is not going to move. And if it is not moving, we can say it is in translational equilibrium, and you can call this one, that is the first condition for an object to be at equilibrium. Because remember, we said for an object to be at equilibrium, there are two conditions. First, the net force on the object must be zero. Second, the net, we can say the net torque on the object must be zero too. Now, that is the first condition. What about the second condition here? The second condition is, if an object is at rest, what is the angular speed of the object? It is obviously zero. If the angular speed is zero, we can also say the angular acceleration will be zero. If that is the case, then we can say the net torque is also zero. If the net torque is zero, then that is the second condition of equilibrium. So if an object is at rest, it is already at equilibrium. So don't forget, as long as it remains at rest, it is at equilibrium. That is first. Second, what if the object is moving? Then that is the point where you have to pay extra attention to, because objects can be at equilibrium not only if they are at rest, but they can be at equilibrium even if they are moving. How? Let me tell you how. We said if an object is moving, it must keep moving at a constant motion here. When we say at a constant motion here, if it is moving in a straight line, all right, if it is moving in a straight line, it must keep moving in a straight line at a constant speed. Okay, so if it is a straight line, we can say this, constant motion. If that is the case, if the object is moving in a straight line, let's just say straight line here, this arrow represents a straight line. If that is the case, we can say V initial of the object must be equal to V final of the object. In other words, there is no change in motion here. If there is no change in the velocity or the motion of the object, no change, then we can say the acceleration is, if the change is zero, then we can say the acceleration is zero. If the acceleration is zero, we can say the net force is zero. If the net force is zero, and that is the first condition of translational equilibrium. But don't forget, when we say translational equilibrium, if it is moving, it must keep moving at a constant velocity. Don't forget, the direction must also remain the same as well. Even if the velocity is the same, there's no change in the velocity or the speed here, but if the direction change, it is not in translational equilibrium. What about if an object is moving? In that case, the object is moving, but it shouldn't speed up or slow down or change direction. It shouldn't do any of those. What if the object is moving, but let's say rotating this time? If it is rotating, it must keep rotating, but at a constant angular speed, let's say. So if that is the case, we can say omega initial must equal to omega final. If that is the case, then there is no change in angular speed. If there's no change in angular speed, then we can say angular acceleration is 0. If angular acceleration is 0, then we can say the net torque is also 0. Because later on we're going to study an equation here where it says net torque, which is similar to this one here, but in rotational motion, it is equal to moment of inertia times angular acceleration. But for now, we can say if the angular acceleration is 0, then the net torque is 0. In other words, we can say the object now, it is at a rotational equilibrium as well. Okay, I hope these are clear enough. If not, perhaps maybe I can give you one more idea for this one, for an object to be at, let's say, total equilibrium. So let's say we have a seesaw here, okay? This seesaw, it is at rest. What does it mean if it is at rest? That means, first of all, those forces that are acting on the object, let's say a child is here, so there's a force downward, another child is here, there's another forces downward. This seesaw itself also has a weight as well. So these forces that are acting on the seesaw, all of these are applying a push downward on the seesaw. You agree with me? But in order to balance this one, this support has to apply a force upward. It has to be equal in magnitude to these three forces, but opposite in direction so that it can balance out. We can say if the forces that are downward equal to the forces that are upward, then we can say there will be no motion here, and we can say the net force equal to 0. When we say the net force, of course, we can say the forces that are downward if plus the forces that are upward, let's say upward first, plus the forces that are downward, the total, if the total is 0, then we can say the net force is 0. That is called translational equilibrium. All right, that is one thing. What about rotational equilibrium? If for the same seesaw here, now this is the axis of rotation. This person is trying to rotate it clockwise. This person is trying to rotate the seesaw counterclockwise. If the torque of this one equal to the torque of the other one here in magnitude but opposite in direction, then this seesaw will be in rotational equilibrium as well. So we can say if the torque of the clockwise person, if it is equal to the torque of the counterclockwise person, if these two are equal in magnitude and opposite in direction, then we can say the net torque, it is equal to 0, because the net torque, it is equal to, we can say the net torque, it is equal to the torque that is clockwise plus the torque that is counterclockwise. Then if this is 0, then the object will be in a rotational equilibrium. What about an object? This is, we can say, for an object that is at rest. What about for an object that is rotating or moving here? Let's say we have a car that is moving. If this car is moving in a straight line, but if it doesn't speed up or slow down, so V initial will be equal to V final, and it doesn't change direction, in that case, we can say the object is at equilibrium, because if that is the case, the net force on the object will be 0. In other words, if these two are equal, what is the acceleration here? The acceleration will be 0. If the acceleration is 0, F net will be 0. What about the same, let's say we have a turntable this time. This turntable is rotating. Okay, will it be, or when will it be at rotational equilibrium? We can say if this turntable is rotating at a constant angular velocity. In other words, if we take a point, angular speed is, this point it is a value, right? Let's say 10 radian per second. And if this point go to this point here or to the other side here, if the angular speed, you can call it final. If it is still the same thing, which is 10, there is no change in angular speed, then you can see that it is still rotating in the same direction. So no change in angular speed. If that is the case, we can say the angular acceleration is going to be 0, and then we can say the net torque is going to be 0 as well. These are the two conditions for both rotational and translational equilibrium, but what is most important here is just remember this. For an object to be at equilibrium, if the object is at rest, it must remain at rest. Then in that case, it has both types of equilibrium, translational and rotational. If the object is moving, then it must keep moving at a constant motion in order for the object to be at both translational and rotational motion. By the way, it is possible for the object to be at one of these types of rotational or translational equilibrium, but not the other. For example, like a football, if it is thrown in the air here. And because thrown in the air, and because of the air resistance, this football is not rotating, it is just moving through the air. But because of the air resistance, the motion of the football, it is going to slow down. If it is going to slow down, clearly there is some net force in here, so we can say the object is not at translational equilibrium. But is the object rotating? No. If it is not rotating, we can say the torque that is clockwise equal to the torque that is counterclockwise, and then we can say the net torque is 0. So for this example, it can be at rotational equilibrium, but not in translational equilibrium because it is going to slow down here. All right, now let's get back to what we have. Let's get back to these points one more time. These are exactly everything that I wrote for you here, and I hope you wrote them down here. The two conditions for equilibrium, because you will be asking, Wazari, what are the two conditions of equilibrium? The first condition we have is, we said, it doesn't matter which one you consider them first, as long as you mention the two here. So we can say the net force must be equal to 0. This is a Greek letter, it's called sigma, represents the net or the sum of the forces here. The sum of the forces, by the way, equal to 0. If that is the case, we can say the object is at translational, and this is for rotational because we have torque. If the net or the sum of the torques is equal to 0, then we can say the object is at rotational equilibrium. And these are some extra explanation that I just told you. And these are some diagrams and simplifications of what I just said here. For example, this is a seesaw. In order to be at rotational equilibrium, the torque of this side must equal to the torque of the other side. So counterclockwise, you can say. If it is equal in magnitude and opposite to the clockwise rotation, then this two, or the seesaw, will be balanced. That is at this point, we can say it is in rotational equilibrium. What about the second case in here? All right, for the second case, we can say, okay, give me a second. For the second case here, okay, for the translational equilibrium, we can say all the forces that are acting downward must equal to all the forces that are acting upward. Then if the total or the net is 0, then we can say the object is at translational equilibrium. And then there are some other examples which I would like to, perhaps maybe it would be easier to explain these cases once we have a question, but I'll tell you anyway here. If this bar that is suspended at one end here, then clearly there will be center of mass for the object here. So this one produces a counterclockwise torque. There must be something else to hold it still so that it doesn't rotate if it is in rotational equilibrium. In simple method or words, you can say the torque that is counterclockwise must be equal to the torque that is provided by this thing if it is attached or there's a string or whatever that is at this point here. And you can even simplify for translational equilibrium. You can say the forces that are acting downward must equal to the forces that are acting upward. But there's one more thing you have to be careful. Now, if we have forces from the side as well, like the sides for translational equilibrium, these forces, let's say the forces that are to the right must be equal to the forces to the left, so that these can cancel out. If they cancel out, that means they are in equilibrium. If not, then that means they're not. Okay. We have a question here, says, what are the two conditions of equilibrium? This part of the question has been in Uzari so many times. We said the two conditions for equilibrium are, we said the net force must be or must equal to 0 for translational. For rotational, the net torque must equal to 0. That is the answer, or you can say the answer to the first part of the question. Second part says, explain how they apply to children attempting to balance a seesaw. So consider now there are two children here on either sides of a seesaw, how they can attempt or try to balance the seesaw using these two conditions. Well, first of all, if we talk about the condition of the translational equilibrium, we'll say these two children apply a force downward. Let me draw a diagram. Maybe you could draw this diagram too, just to help you remember or makes it easier for you. That is, we can say the first one here. This is a seesaw. This is the first children here. This is the second children. We can say the force of the children, these are downward. And also the weight of the seesaw, these are also downward. These downward forces must be equal in magnitude and opposite to the force that is provided by the support in here. So if I do this one, like if I add all these three forces together, these are downward forces, must be equal to the upward force, then the seesaw will be balanced. But who's providing this upward force? We can say the normal force or the support is providing this upward force. That is the, we can say, first condition for equilibrium, or this is how they can attempt to balance the seesaw. What about for rotational equilibrium? For rotational equilibrium, this child is trying to rotate this seesaw clockwise. The other one is clearly rotate the seesaw counterclockwise. So if their torque is equal in magnitude and opposite in direction, then the seesaw will be balanced, and that's it. All right. Now we have a section review question. This is also one of the questions that's been in Wizari several times, we can say. It says, which of the several positions indicated in the figure should the supporting pivot be located to produce the following? Okay, so to produce a net positive torque, and then after that to produce a net negative torque, and then at which one of these locations there will be no rotation at all. So let's take a look at this one. First, we can redraw the diagram at this point, and then we can try solving this one here. So this is what we have. First of all, perhaps we can redraw the diagram at this point. Let's say this is the diagram that we have, and we have forces. One of the force that we have, it is 50, and then the other force that we have, it is 150. These are in newtons here. How many supports do we have, or can we have at this point? We can have 7 supports. All right, let's say this is one of them. 1, 2, 3, and then 1, 2, 3. I hope the distance, by the way, must be the same, all right? But this is just for the sake of the drawing here. So this is A, B, C, D, E, F, and G here. Okay, so once again, the question says at which one of these locations there will be a net positive torque. Remember, first of all, this one is trying to rotate the seesaw this way. So clearly, this 150 Newton causes a negative torque here. What about this 50 here? This one causes a counterclockwise rotation. Counterclockwise rotation, which is going to be positive. Okay, but here's a point. If you remember, previously we've mentioned that even at this point, in order to balance something, the heavier object must always sit closer to the axis of rotation. You can write this as a note here. In order to balance something, especially when we have a seesaw and there are children there, the object that is heavier must always sit closer to the axis of rotation. All right, so at this point here, watch this. Would it be wise if I start from point A or choose point A as the axis of rotation? Oops. Right? If I make this one as the axis of rotation, this is a small force. So, and the distance is also small. So obviously the torque that I'll get is going to be small. And this force is bigger, and then this distance is bigger. So that is way obvious that this one will rotate the beam, and as a result, I'll get a negative torque. So what can I do at this point? I'll start all the way from the other end. I'll choose this one as the axis of rotation. I'll choose this point as the axis of rotation. What happens if I choose this as the axis of rotation? Now clearly, we can have torque at this side and that side too here. So we can say the torque that is provided by 50, it is equal to what? It is equal to force times distance. You already know this one. What about the torque that is caused by 150? That also equals to force times distance. True? All right, so if I choose this point as the axis of rotation, how far am I from that point? You can consider each one of these distances to be 1 unit. 1 unit what? Is it 1 centimeter, 1 meter, 1 kilometer? We don't care. You just count the distance, because whatever the distance is, at the end, the units will cancel out. So it is the same thing at this point. So, but if I start counting this, how far is this from the axis of rotation? And don't forget, we've learned this when we were studying torque. We said the distance is always where the force is acting to the axis of rotation. So if I count, that would be 1, 2, 3, 4, 5, 6, and 7. So we can say the force that I have 50 times 7. What about the other side here? So this force that I have, it is 150. How far is it from this one here? It is only 1 here. All right, so now what about the total or the result of this? That is going to be 350 Newton Newton meter, that is going to be counterclockwise, which is positive. What about the other one? It is going to be 150 Newton meter, but this is clockwise. You can call it negative if you want to. But now, if I want to find the total or the net, we know that the net, it is equal to what? Equal to the torque, that is, you can call it torque 1, torque 2, doesn't matter. All right, let's just call it torque of 50 plus the torque of 350. So the 150 produces, the 50 Newton torque produces 350 plus the other one, because it is clockwise, we're going to use negative what? Negative 150. All right, so now once you find the result in here, that is pretty obvious, right? That is going to be 200. Okay. 50 times 7, yes. All right, so that is going to be 200 Newton meter, and clearly it is positive. So we can say at point G, I'll get a positive net torque. Don't forget, at what point? Point G. But will I just find point G and then leave it there? No, because I'll have to try other points too. Who knows, maybe I'll get a positive torque at point F and more than one point. So let's find out. But for now, just remember, at point G, okay, we'll get a positive torque. Okay, that is one. Now, what about, let's try another point here. All right, what other torque? What about if I use this point as the axis of rotation now? This point here. Let's see if we can, let's erase this one. All right, so now we'll do the same thing. Let me erase this one too, because these answers will change now. And then this one too. Okay, so if we use point F as the axis of rotation, how far 50 would be from point F, or support F, you could say? That is going to be 6. So 5 times, or 50 times 6, that is going to be 300. What about this one? How far is it from 150? That is going to be 1, 2, right? So 150 times 2, that is going to be 302. So now the counterclockwise torque is 300 and the clockwise torque is 302. So what do you think the total, the net torque is? It is going to be 0. If it is 0, can I say there will be no rotation? Because this torque, it is equal to this torque, so there will be no rotation at point F. And if you look at the choices here, it says at which one of these points there will be no rotation. That is going to be at point F at this point here. So no rotation at point F. So clearly we can say at point F there is no rotation. Because it is at rotational equilibrium. Now what about, there is more. Part B says, where can we have a negative torque? And let me tell you this. Now we know that at point F, it is at equilibrium. What do you think will happen if we keep moving to the left at this point, right? Well, if it is at equilibrium at this point, if we go to the other side, we'll be even further from the 150. So the distance gets larger. So obviously this 150, it is going to rotate the beam clockwise. But let's do some numbers, see how it end up, or what is it going to be like. All right, so point F, how far is point F from this 50? 1, 2, 3, 4, 5, yes? So that is going to be 50 times 5, that is 250 Newton meter. This is counterclockwise. What about 150? It is going to be 3 units far, 3 points or whatever far from this. So 150 times 3, right? That is going to be 450. Is that true? Newton meter. So you can clearly see that 450, it is way bigger than 250. So in which way do you think this beam is going to rotate? Clearly it is going to rotate, clearly it is going to rotate clockwise here. If not, you could just find the net torque if you want to. The torque of 50 plus the torque of 150. So the torque of 50 is 250 positive plus minus 450. So can you see the difference here? So clearly this one is bigger. In that case, of course, the result is going to be negative, which means that the seesaw is going to rotate clockwise. All right, well, if it is going to rotate clockwise at point E. What about point D? Because we're getting even further and further. So can I say from point E all the way to point A, the beam will rotate clockwise? Yes. But of course, if we go by the order, I can say from point A all the way to point E, it is going to rotate clockwise, or the net torque is going to be negative. And I hope you understood this one here. All right. And here's the solution you can see as well. All right. So these are what we have. A net positive torque. We said at point G, if we make point G as the axis of rotation, then these are the torques that we have. If you want to find the total, it's going to be 200, and that is positive, which is going to be counterclockwise. At point F, we said there will be no rotation because the two torques are equal in magnitude and opposite in direction. At point E, it is going to be negative 200. Well, now from point E all the way back to point A, it is going to be a negative torque. If not, you could just like rearrange it. You can say from point A all the way to point D, it is going to be a negative net torque here. All right, now we have this question, or some of these questions. I believe the first one is very easy. Let's try solve a few of those here. It says the object is completely in equilibrium, right? If it is completely equilibrium, these are the two conditions, right? Which one of these do you think it is the correct answer? That is going to be option B. Now, question 2 is also important. I need you to take some notes here. It says, in which of the following situation both equilibrium condition, rotational equilibrium and translational equilibrium, are not achieved? Make sure when you see a keyword like this, even in Wizari, you underline that, or you put that in a circle or in a box like this, because sometimes once you read the options, you forget that it was not maybe sometimes says correct or incorrect, because of course we have situations where because of lack of attention, sometimes you just don't see the word here, and of course you will end up losing 2 marks very easily. So this point here says, which one of these are not achieved? It says a bicycle wheel rolling along a level highway at a constant speed. And if you remember, we said whenever it mentions constant, we can say constant speed. That is obvious. It is going to be at translational, both types of equilibrium. But why both? All right, does it mention both? Let me tell you this. If it says at a constant speed, we can say, in this case, can I say V initial must be equal to V final? Yes, if that is the case, then because it is at constant, so acceleration is 0, the net force is 0. If the net force is 0, it must be at translational equilibrium. What about rotational? This says a bicycle wheel. All right, we know that. What is the relation between translational and angular? It is tangential, it is equal to angular times the radius. All right, so let's say omega initial, it is equal to V initial over the radius. The radius of the wheel doesn't change, yes? What about omega final? Isn't it equal to V final over the radius? All right, well, V initial and final are equal. Radius of the wheel doesn't change, so aren't these two also the same? Yes, so we can say omega initial and omega final are equal, then we can say the object is in rotational equilibrium as well. So don't forget this. Because the radius or the wheel of a bicycle is a rigid object, so clearly the radius is not going to change. All right, so let's not forget this. So this one has both types of equilibrium. That is not what we're looking for. B says, a bicycle parked against a curb. A curb, that would be something like a recif, Basha. All right, so this point we said if an object is at rest, immediately it is at both types of equilibrium. It has both types of equilibrium, both rotational and translational. It says parked, okay? So it is at rest. Now, C says the tire of a braking automobile that is still moving. If it is braking, clearly omega initial is not going to be equal to omega final. If that is not the case, then there is acceleration. If there's not 0, if that is the case, there will be some net force. Let's not go through a lot of details. Whenever the velocity is changing or the speed is changing, it is not in translational equilibrium. And once again, because it is a wheel of a car in this case, the radius does not change. But if these are changing, omega initial and final will change too. So it is not in rotational equilibrium as well. So we can say this is the one that we're looking for here. So this one, it is not in both types of equilibrium. Can we say A and B now? Because we said these are both in equilibrium. All right, so the correct answer is option C. All right, now what else do we have? We have, okay, clearly we have a technical issue. I hope not. We're back, I guess. Not fully. Is it off? No. It might need a minute. All right, it is back. Okay. Well, maybe because of this. All right, so that was a very good question. Question 3 is also very interesting. It says, which one of the following statement is correct for an object rotating with a constant angular speed? If it is rotating with a constant angular speed, it says the net torque acting on the object is equal to 0. It says which one of this is correct? Don't forget. If it is rotating at a constant angular speed, don't forget, that means omega initial equal to omega final, so the net torque immediately is equal to 0. If that is the case, then the object must be at a rotational equilibrium. Very good. So the first thing says the net torque acting on the object is equal to 0. That is true. What about B? It says the net torque acting on the object is not equal to 0. No, if it is constant angular speed, the net torque must be 0. C says the object is not at equilibrium. That is incorrect because the object must be at equilibrium if it is at a constant angular, or if it is moving or rotating at a constant angular speed. D says there is no torque acting on the object, and that is incorrect. If the net torque is 0, obviously the torque that is clockwise and counterclockwise must be equal. All right, question 4, that is easy as well. We went through this one before. Now, we have question 13 says, what must be true about the velocity of a moving object to be at equilibrium? Remember, we said for an object to be at equilibrium, there are 2 things you need to know. First of all, if it is at complete equilibrium, it must be at both translational equilibrium and rotational equilibrium. And when do we get, or when do we achieve translational equilibrium? If V initial equal to V final, the object is neither speeding up or slowing down, and it should remain on the same path, same line. There shouldn't be any change in direction. Then the object will be at translational equilibrium. What about for rotational equilibrium? The object, or we can say the torque that is clockwise, must equal to the torque that is counterclockwise. In other words, we can say the angular speed of the object must remain the same. In other words, an omega initial and omega final must be equal. Then there would be both types of equilibrium. All right, we also have another question which is also interesting. It says a uniform 40-meter board supports 2 children. One weighs 510 and the other one weighs 350. The support is under the center of mass of the board and the 500 Newton child is 1.5 meter from the center. So the first question says, where should the second child sit to balance the seesaw? All right, that is a very easy question. Let's solve this one together. All right, this is what we have. Let's say this is the seesaw here. Okay, so here's the support. There are 2 children. Or first of all, let's not forget this. The weight of the seesaw, it is 40 Newton. And you can also take a note or write this as a note for yourself. Whenever we have something or the question tells you a uniform something, if it has the center of mass, it is always at the center. Don't forget this. All right, that is one. So, and then it says the 2 children, one of them is 5'10". So here's 5'10", let's just say. And then the other one is 350. Okay, the support is under the center. The 5'10", it is 1.5 meter. 1.5 meter from the axis of rotation. And clearly, if this person is heavier, it must be sitting closer to the axis of rotation. We can say this distance, that because this forces or weight is less, so this child must sit further from the axis of rotation. In other words, the distance that we're going to find here, it must be bigger than 1.5. If it is not bigger, then double check your work. You must have done something incorrect. Okay, the question says, where should the second child sit to balance the seesaw? So to balance the seesaw, we can say the net torque must be equal to 0. In other words, we can say the torque that is clockwise or counterclockwise, doesn't matter, must equal to the torque that is clockwise at this point here. But we know that torque is equal to force times distance for this side, and we can say force times distance for the other side. We can say the force of child 1, distance 1, F2, distance 2 here, and that's it. So this is 510 times what distance? 1.5. It is equal to 350, all right, times D2, we can say. Can you find D2? Yes, D2, it is equal to whatever is 510 times 1.5 divided by 350. Then you can find this distance, and let's see what is this distance equal to. This distance equal to, it is equal to 2.2 meter. See? If you remember, we said this distance must be bigger than 1.5. So 2.2 meter, it makes sense. It is bigger than 1.5 and it is reasonable. Part B says, how much force does the support exert on the board? That is also a very good question here. Now, how much? Because the question this time is about the force here. All right, because the question is about the force. Can I say the forces that are acting downward must equal to the forces that are upward? Yes, so this will be the second condition of equilibrium. The force or the net force, it is equal to 0. In other words, we can say the forces that are upward, we can say must be equal and opposite to the forces that are downward. What is the force that is upward? All of these are applying a force downward. So let's erase the distances here because we don't need them anymore. The question is about the forces now. So in this case, all of these forces are acting downward. In order for this to be at equilibrium, don't forget this. Oops, should have done this one here. All right, so now this support must apply a force upward, and you can call it F normal here. So we can say F normal, it is equal to the downward forces. What are the downward forces? You can call them F1, 2, 3, doesn't matter. Or if not, you could just write the numbers here. 510 plus 40, don't forget the 40, plus 350. Okay, so what is the result of all this? That is 800, right? 860, and this will be the total of 900. Okay, so 900 Newton must be upward. Don't forget this. This is how we can balance the seesaw. First of all, you can always, it doesn't matter which one you start first, clearly. It depends on the question or what the question is asking, but you always use the two conditions to find whatever that is unknown here. We also have another question, which is also interesting, says, why would it be beneficial for a bicycle to have a low center of mass when the rider runs or rounds a turn here? Let me give you an explanation for this one as well. You've seen clearly on TV that when there is a bike race, once they get to a corner, they kind of like tilt or kind of like shift their body, sort of tilt themselves up so that they can round the corner safely. Why do they do this? Or what does this has to do with the center of mass? Let me give you perhaps one example here. So let's bring shape, consider this. These are water bottles here. This is one. And let's just copy paste in this one here so that we can have the exact shape. Okay, so imagine these are water bottles. One of them is filled and the other one is, let's say, half filled, or not even half, but consider this. So the center of mass of this one is likely to be somewhere close to this point because this part is not exactly in the center, a little bit lower than the center of the bottle because this part is empty a little. What about this one here? It is likely to be somewhere here. So we can say the distance from the center to this one, it is going to be less compared to the distance here. You might say, but sir, there's less water here. Even if we have the same water, we could draw another shape here. You could have, let's say, had the water bottle just not upside down. Let's say on a horizontal. As a matter of fact, let's see if we could do that. That is the same shape, but upside down. What exactly happens if this one is upside down? Of course, we have to make some changes here too. So let's erase those parts. So now the water is going to be something like this one here. This would be the center of mass is this. So you can see that if it is on a horizontal, the center of mass, or you can say this distance to the bottom is going to be less. In other words here, we know that torque, it is equal to force times distance. And torque is the effect, or you can say the turning effect, true? These have the same mass, or you can say the same force. But what is different here is the distance here. In other words, we can say the larger the distance, with a little bit of rotation, then there will be a large torque. And this torque, it makes, if it is a bicycle, let's say a bicycle or the driver, because the center of mass is high, with a little bit of tilting, that will produce a large torque, and then it will just rotate the whole bicycle. It's just going to fall down, or you can say tip over, all right? But if the center of mass is low, it could be even the same shape here, like this one here, then you can rotate the bicycle, the bicycle can tilt themselves up, right, to a larger angle without tipping or falling over. The reason why, because torque at this point, it is equal to force times the distance here, even if the force is the same, or the mass is the same, but because the distance is small, so the torque will be small, the turning effect will be small, so this one is unlikely to tip over, to fall over, you can say. And this is the benefit of having a lower center of mass. And we have the same thing in Formula 1 cars, you can say, in these sport cars, because these are very fast, especially at the sharp corners here. They must have a low center of mass so that there would be no possibility of tipping over or falling, or you can say just tipping over, you can say, or falling over, whatever you call that. All right, so once again, is it possible to, not this one here, is it possible to balance two objects? Where's the bicycle question? Here. So it says, why would it be beneficial for a bicycle to have a low center of mass when the rider rounds a turn? We said the lower the center of mass, the smaller the lever arm, making the bicycle more stable and less likely to tip over easily. All right, we also have another question, says, is it possible to balance two objects that have different masses? Once again, the answer is yes. But how can you balance them? We said the heavier object, or the object with a bigger mass, must always sit closer to the axis of rotation. And then you could just adjust their distance until the two things will be balanced, and that's it. Just for example, like two person on a seesaw, one of them is heavier than the other one. The heavier one must sit closer to the center or to the axis of rotation so that they can balance the seesaw. All right, question 17 says, a particle moves in a straight line. Don't forget this. A particle, you can say an object, like a car, it doesn't matter. If it is moving in a straight line, and you're told that the torque acting on this particle is 0 about some axis of rotation. Okay, or about some unspecified origin. Does this necessarily imply, means that the total force acting on the particle is 0? The answer is not. Imagine if a car is moving forward, okay? And you're told that, let's just perhaps do it horizontally here. A car is moving forward, and you're told that the net torque acting on the object is 0. In other words, we can say the torques that are clockwise, it is equal in magnitude and opposite to the torques that are counterclockwise. So this particle, this object, it is not rotating or not tipping over because the object is moving in a straight line. Okay, so the question says, does this necessarily imply, means that the total force acting on the object is 0? The answer is no, because this object, while moving in a straight line, it could be speeding up or slowing down. So it has nothing to do with the rotation at this point. So just because the rotation or the net torque is 0, does that mean the net force is 0 too? Not necessarily. this car, this person, this object, this point, particle could be under the effect of a net translational force. It could be speeding up or slowing down. So the answer is no. It could be under the translational net force. It might be accelerating, speeding up, or slowing down. But there is another part of the question says, can you conclude that the angular velocity of the particle is constant? The answer is yes. Even if it is rotating, let's say, because the net torque is 0, then omega initial must be equal to omega final. That is the only case where the net torque is 0. If these two are not equal, then the net torque will not be 0. So once again, can we say the angular velocity is constant? The answer is yes. But for angular velocity to be constant, the object must be rotating, don't forget. But this rotation, it has to be constant. Just you can, at this point, you can think about the motion of the tire of a car, for example. If it is moving at a constant velocity, the rotation of the tire, it is neither going to speed up or slow down. It will rotate with the same angular speed, and in that case, we can say the net torque on the wheel or the tire will be 0. There is another example as well. This been in Uzadi once. It says like a football in the air. And we've mentioned previously that a football in the air, watch this, because it is in the air, it is going to slow down because of the air resistance. So that means the net force is not 0. But if it is not rotating here, or even if it is rotating at a constant angular speed, then we can say the net torque is equal to 0. Okay? Because in that case, it doesn't speed up or slow down in rotation. All right. Now, we have another question, question 19. It says, an object rotates with a constant angular velocity. Okay. Can there be, okay, let's hide this one so we can see the entire question here. It says, if an object is rotating at a constant angular velocity, can there be a net torque acting on the object? As long as there is a constant angular velocity, what does it mean, constant angular velocity? Can I say omega initial must equal to, or it is equal to, let me just get rid of this thing here. All right. Seems we don't want at this point. Constant angular velocity, that means omega initial, it is equal to omega final. If that is the case, the angular acceleration is 0. And if that is the case, we can say the net torque on the object must be equal to what? Equal to 0. So the question says, can there be a net torque acting on the object? The answer is no. Explain your answer. We said no, constant angular velocity implies or means that there is no net torque. Otherwise, the object's angular velocity must change. Now, we also have another question says, if an object is at rest, can you be certain that there is no external torque acting on the object? The answer is no. This is also a very good question. Just because you see an object is at rest, does that mean there is no torque on it? No, by the way, we're not talking about the net torque. We're just talking about the torque. If an object is at rest, does that mean there is no torque on it? We cannot be certain, because what if there are some torques on this one, but they are equal in magnitude and opposite in direction? Then they'll cancel out, then the net will be 0, and that'll be exactly this. So if you see an object at rest, we cannot be certain, we cannot be sure if there is no torque acting on the object. There might be some torques, but these torques might be equal in magnitude and opposite in direction, and they might cancel out. This is why the net torque is 0, and this is the reason why the object is not rotating here. Okay, I believe that'll be the end of this session. Inshallah, next time we're going to start with the sample problem. There are some good questions here, and of course, we can say at the verge of solving real problems concerning both rotational and translational equilibrium. Till then, keep watching or stay tuned. I'll see you soon, inshallah. Assalamu alaikum wa rahmatullah.